Hi students, hope you are doing well. So today we start lecture 60 in our course, and today I'm going to discuss the different type of orbits or trajectories which can be there for a spacecraft. So essentially the spacecraft can follow different type of paths which are essentially conic sections. So these can be circular, they can be elliptical, parabolic or hyperbolic. So today we are going to look at how these trajectories look like and what can we do about these trajectories. So let us discuss that today. I'm Dr. Ranjan Ganguly. So just to review the whole field of space vehicles, what happens in space vehicles is we can classify these vehicles as essentially of two types. So one of the types are those which circle around the earth. For example, you have earth satellites, and these will circle around the earth provided you have a velocity of 7.9 kilometer per second. This is also known as the circular velocity. Now, typically when you want a satellite to circle around the Earth, it has to be in a circle or it can be in an elliptical orbit. In contrast, if you are looking to escape the Earth's atmosphere and get far out into space, you need something which is known as the escape velocity, which is at 11.2 kilometers per second. So essentially, if you have a typical rocket which is going to Mars or to the moon or to Saturn or outside the solar system, you need to impart this with a velocity of at least 11.2 kilometer per second so that it can escape the earth. So this is known as the escape velocity. Sometimes it's also known as the parabolic velocity. We'll look at that later in this lecture series. So today what we are going to do is we are going to look deeply at the orbit equation and figure out its physics and geometry. So let's again take a look at the orbit equation here, and you will immediately realize that this is the equation of a conic section. Now typically when we study conic sections in coordinate geometry books, we study it in Cartesian coordinates, that is in x and y system. But this equation I have written here is the equation of a conic written in polar coordinates. So essentially we are now using r and theta. And this nomenclature helps because whenever you are dealing with something to do with the earth, it's circular. And so polar coordinates are very suitable as far as the earth is concerned. So if we look at this equation for the conic section, we will see that the type of trajectory or the graph which you obtain if you plot this will depend on the value of E. So E is known as the eccentricity of the conic section. If E equals 0, this path is a circle. If E is less than 1, the path is an ellipse. If E equals to 1, the path is a parabola. And if E greater than 1, the path is a hyperbola. So once again recall that the orbit equation we had obtained after solving it was r theta is this equation here, and when we set P is h square by k square and we set E is a h square by k square, we were able to convert this equation into this equation, which is essentially the equation for a conic section. So essentially in this equation we have removed the physics out of the problem. We have separated the physics here in terms of P and E, and so the equation is represented in a purely mathematical form. So we have to actually calculate some of these parameters such as C, and one of the ways to calculate it is to use something known as the burnout condition. For example, if we take this equation for R and we can say that at R is RB, theta is 0. So this is from convention. So therefore what happens is that I can take this equation for R, plug R is equal to RB, theta equal to 0. So I get the denominator as 1 plus E cos minus C. Now I can solve this equation for C if I know the values of P, E and RB. So essentially RB would be something which would be known to you. So this is typically expressed in kilometers. You can convert it to meters, and once you do that you can obtain the value of C, and then after some time doing more manipulations you can also obtain the values of H, A, E and all the other parameters which govern this conic section. So let us start looking at all the special cases for this conic section, starting with the simplest one, which is the circular path. So when you have the circular path, E equals 0. So if I substitute E is 0 here, I typically will just get R is equal to P, because this term involving cos theta minus C will become 0. Now R equals to P is the same as R equals to h squared by k squared. So this is going to be a constant, which is the equation of a circle. So you can see that when E equal to 0, you get the equation of a circle. Also, you can see E0 means that this term is going to be 0, and therefore A will be 0 provided h square by k square is not 0, which is typically the case. So if we now try to plot this path, we can say there is a mass here. This is the Earth, capital M, and you have the mass small m here, which is the space vehicle here. So now you can see that the path is going to be like this, where R is h squared by k squared. That's the value of this r radius here of this circular path. Now here I have put the burnout condition. So essentially burnout is taking place at this location, B equals burnout. Here R is RB, and this angle is C, and this angle is theta. So essentially we have already seen that theta is 0 at burnout at this position here. So theta starts from here. C is the phase which exists between the x-axis and the burnout point, and the burnout is going to determine the values of C, H, and A. So that is typical for the orbit equation. So also you can see here velocity is Vb at burnout, and at some point here the velocity of the spacecraft is given by V. Now let us look at the next orbit, which is the elliptical orbit, and in this case of course the value of E will be between 0 and 1. Now, of course, when the value is 0, you get the circular case. So that would be the equal case. But in general, if you have it between any value between 0 and 1, you get an ellipse. So essentially what happens is that then R is given by P by 1 plus E cos theta minus C. You cannot get a very simple formula here, but you can say that this value 1 plus e cos theta minus c will be bounded between 0 and 2, because remember that cos is going to be bounded between minus 1 and 1. So the lowest value this term can have is negative 1. So that will give you the 0 as the lower bound, and the highest value this term can have is going to be 1. So that's going to give you 2 as the higher bound here. Now the elliptical orbit is going to look something like this here. So essentially this is a typical orbit which many of the satellites have as far as the system is concerned. And here again you have the burnout point, and you have the point here of this velocity V, and you have RB here, and you have this angle C and theta. So essentially whenever E lies between 0 and 1, you are going to get the ellipse as the path. Now both the circular case and the elliptical case, which involve E existing between 0 and 1, they will result in paths which are essentially circling or orbiting around the planet concerned. If E is equal to 0, you will get the circle, and if E lies between 0 and 1, you will get the ellipse here. So now let's look at the remaining two paths. So let's start with the parabolic path, and the parabola happens when E equals 1. So in the orbit equation, let us put E equals 1. So we do that here. So we simply get R is P by 1 plus cos theta minus C, and also we get the equation 1 equals A h square by k square. So these are two simplifications which we get here. And the parabolic path is essentially going to look like a parabola here. So this is the equation of R equals P by 1 plus cos theta minus C. So I have put E equals to 1 in this equation. And again, very similar behavior, but the orbit is quite different. So you have the burnout point here, you have C and theta here, and essentially this body is going in an orbit which is parabolic. So this is a good path if you want to escape the earth. So essentially that's something we are going to look at later. If you want to leave the earth, go to a different planet, then parabola is one way to go. Now the second way you can escape the earth and get out in space is by using the hyperbola, and the hyperbola corresponds to the situation where E is greater than 1. So essentially again we have R here, but now E is greater than 1. So again this of course is kind of unbounded here. So all that we can say is that this denominator term is going to be greater than 0 because cos is going to vary between -1 and 1, and so the value here is going to be dictated by that. So that's something we have to concern, and therefore we have to keep in mind that this hyperbolic path is also possible. So again, the fact that a h square by k square is greater than 1 will also typically exist. Now the hyperbolic path is given in this manner here, and you can clearly see here that is the burnout and this is the velocity here in the hyperbolic path. So the equation now is given by r equals p by 1 plus e cos theta minus c, and the curve here is the hyperbola. So today's lecture is very important because it gives us some physical and geometric feel about the orbit equation, about the trajectory of the spacecraft out there in space. So we saw that the equation for the trajectory is given by the equation for the conic section in polar coordinates. So that equation was r is p by 1 plus e cos theta minus c. So this is an equation you can commit to memory. Remember, p is h square by k square and e is a h square by k square. Now this value of c comes from the burnout condition r equals rb, and the type of orbit or trajectory you get is going to completely depend on the value of E which you have in the particular equation. So if E is 0, you get a circle. If E is less than 1, you get an ellipse. If E equals to 1, you get a parabola. And if E greater than 1, you get a hyperbola. So depending on the requirement of your mission, you can choose the value of E. If you want to circle the Earth, you choose E equal to 0. If you want to put the satellites into an elliptical orbit, you have to choose E less than 1. If you want to exit the Earth and go to some nearby planet, you can use E equal to 1, which is the parabolic exit trajectory. And if you want to exit the Earth in the form of a hyperbola, you can choose E is greater than 1. So depending on these values, you will get the particular trajectory or orbit which you want. So today we saw that the orbit equation is extremely important for space flight. So again, if you are a fan of Star Trek, you would know that space is the final frontier and you want to get out in space. So if you want to get out in space, you want to have E equal to 1 or E greater than 1, and therefore if you want to get out in space, you have to follow the parabola or follow the hyperbola. If you are somebody who is content with being around the earth, then you essentially use the circular or elliptical path, and then you can use E is 0 or E is less than 1 but greater than 0. So these will give you the circular and elliptical paths respectively. Now, of course, remember that the mathematics is of course very general. The fact that we are considering the earth is only coming in from the k square value. So remember, k square equals to capital G into capital M, and these are values which you can get for earth. But if you are in Mars and you want to escape that planet, you will have to calculate k square for that planet and use it. And if you are on Saturn or if you are on some planet far out in the galaxy somewhere, you will have to use the k square value for that particular planet. But the expressions are pretty general and you can use it for any system which is out there in space. So I will end this lecture today. In our next lecture, we are going to do the intense math which is required to actually come up with the expression for E, the eccentricity, and then we are also going to derive the expressions for circular and parabolic velocity which are required to circle around the earth or to escape the earth. So I'll see you in a video at that point. See you then.